All right, and welcome everyone. Thanks so much for joining us today for this 60-minute webinar on Introduction to PASCO Capstone. Over the next hour, I intend to show you what I think are the foundational skills for using PASCO Capstone software to collect, analyze data from PASCO sensors. A little bit more about PASCO Capstone in a moment, but to do that, I plan to demonstrate two main activities and have a few little sidebars about more interesting, additional interesting content. The first activity is going to be looking at a mass on a spring oscillating, and for that, we're going to focus on how do we connect sensors, collect data, and display kind of the fundamentals of getting that data in a way that we can display it and do some analysis. In the second, longer, more complex activity, we're going to take a look at an impulse and momentum investigation to see if we can find a relationship, discover a relationship between impulse and momentum for a cart. And there we're going to really focus on how we can control measurement data collection and how we can do a much deeper analysis into the data. We'll be taking pauses with interludes throughout to highlight some of the questions that you asked to make sure that's addressed if it's of general interest question. So keep those questions coming in the Q&A panel. And we'll discuss things like saving files, sharing data and images out of Capstone. We'll discuss the sensor lines that PASCO Capstone supports. Quick answer, all of them from PASCO, even back to the last millennium, and talk about where you and your students can get experiment resources. So a little bit about PASCO Capstone. Capstone is our advanced data collection, display, and analysis software. It's used across upper secondary and college university grade levels, primarily in physics and engineering, where many of its features are focused. But we do know that there are biology, chemistry, environmental science teachers also using the software because of its advanced analysis capabilities for data coming from PASCO sensors across the subject areas. It's available on computers only, so it's available on Windows and Macintosh and works pretty much the same across those two platforms. And it's available for purchase two ways. One is to purchase the site license, and the site license is applicable for all the computers managed by a whole high school site or by a college university department. It's a one-time purchase. We're now up to PASCO Capstone version 2.12. Came out with version 1.0 in 2012. And if your school or department happened to purchase it those 13 years ago, you just had that one-time purchase, got the access code for it, and you've had free updates in those intervening 13 years. There's a newer way to get PASCO Capstone as well. It's called the personal license. The personal license is just for 1 year. Many times students get this, so it's not auto-renewing. It's just 1 year at a time. And it's available from the respective app stores for Windows, that is the Microsoft Store, and for Mac OS, it's available on the Apple App Store. It's roughly the local equivalent of $1 for access to the full features for a year. If you want to learn more about PASCO Capstone, I invite you to go to pasco.com/capstone for information and links to the store links and some more useful links to things like the help system. Talk about later. This session is focused on PASCO Capstone software, but I think it's worth mentioning that we have other data collection and analysis software for our sensors. They include the general purpose SparkView, which runs on everything from Windows Mac to Chromebook, tablets and phones in students' pockets. That's more focused on ease of use over advanced analysis features. And we also last year released a piece of software called ChemView, and ChemView is focused on college level analysis in the chemistry lab. So if you want to compare Capstone to SparkView or ChemView, go to pasco.com/software. All right, but today we're focused on PASCO Capstone. And if you are tasked with making sure that, say, students are comfortable using Capstone, going into the beginning of a lab, I want to point out one resource that's available on the Capstone product page at pasco.com/capstone. If you go to the videos tab of that page, you'll see a number of tutorial videos. And I invite you to take a look at the 14-minute PASCO Capstone Get Started tutorial, which is a nice condensed introduction to the essentials of using PASCO Capstone for data collection and analysis. We'll be diving a little bit deeper than those 14 minutes of content, but it's a nice condensed way to share these features with others. All right, so let us get to the first activity, which is mass on a spring. So I have a 200-gram mass on this spring. You should be able to see in the live video. By the way, if you're joining us live, there should be a handle between the live video and my shared screen that allows you to change the relative size of those to either zoom in on the live video or to look more in more detail at the screen I'm sharing, which right now is slides, but soon will be Capstone. In this investigation, we're going to take a look using a wireless motion sensor, this white box on the tabletop, and the mass on a spring above it, and see how quickly we can analyze data after we collect it and visualize it in PASCO Capstone. So I'm going to launch PASCO Capstone, and we'll talk about what I think is the quickest way to get into visualizing data in PASCO Capstone from sensors. So when we launch PASCO Capstone, new to Capstone version 2 are these quick start options that show up. If you don't like these quick start options, you can just ignore them and proceed as you always do, and we will do that in the second activity. But in this first activity, we're going to take advantage of these quick start options, which are basically quick entryways that set up some things and configure things for us quickly in Capstone. Well, my attention is directed immediately to this sensor data option. If I hover my cursor over it, you may be able to see that there's a tooltip that says connect your sensor and record data in a graph. That sounds perfect for this investigation. So I'm simply going to click on this big sensor data button, and Capstone's going to do a few things behind the scenes. One of those things is to prompt me to connect the sensor. So to do that, it has opened up a panel on the left side here we call the hardware setup panel. And it's basically prompting me, hey, in order to collect some data, we need to connect a sensor. I'm going to be using the wireless motion sensor. So all I need to do is to power on the sensor with its power button. And to better simulate what we'd find in a typical lab, I'm going to make sure we have more than one motion sensor in the room. So I'll turn another on that's at a desk a little off to my right. And we have now 2 motion sensors that PASCO Capstone automatically detects as being available in this list of sensors. Now, the sensors need to be distinguished from each other, so we need to make sure that the one that we're interested in is the one that we're using. And we can do that by looking at the case of any wireless sensor. Bring this closer to the camera, and you may be able to see that every sensor has a 6-digit ID on the sensor, and this 6-digit ID is marked in the software as well, letting us know which sensor is ours. So in my case, it's the one that ends with -716. I'll go ahead and click on it, and Capstone's going to make a wireless connection via Bluetooth to that sensor. Once that sensor is connected, what was a red Bluetooth light is now blinking green, and that says that this particular sensor is now taken by somebody using PASCO software. Now, if I had an experiment that required 2 motion sensors, I could connect to that second motion sensor we see here. But in this case, I'm only going to use 1 motion sensor. I do want to note, though, that my motion sensor, the -716, is now not available to anyone else. A sensor can only be connected to 1 instance of Capstone at a time, though 1 instance of Capstone can connect to multiple sensors if you'd like to for a particular experiment. Well, we're done with the hardware setup panel. So to close it, I'm going to press the hardware setup button. It collapses, revealing something that that Capstone rather did in the background when I chose the sensor data path. And that is it automatically created a full screen graph for me, and it put the primary measurement from the connected sensor for the y-axis measurement of that graph. In the case of the wireless motion sensor, that primary measurement is position, which we can see on the y-axis label, and it defaults to time on the x-axis. Not a requirement, but that's the default, and we'll see how we can change that later. Well, this main space in PASCO Capstone is called the workbook, and the workbook is where we're going to see displays, do data analysis, but the workbook is surrounded on all sides by a couple of toolbars that we can use to do some fine tuning. We have a standard file toolbar and some icons below it that let us access some of those file menu and other menu options more quickly. We see a tab for the page we're on, the workbook page number 1. And then on each side, left, right, and bottom of the workbook, we can see that there's something we call a palette. On the left side, we have the tools palette. That includes the hardware setup panel and some other panels that let us manage hardware and data. On the bottom, we have what's called the controls palette. And in the controls palette, we can do things like record data, change the way we're recording it. And though it's hidden in our sensor data approach, on the right side, we have a displays palette. It's hidden because we don't need it in this case, but we will take a look at that in the second activity. So let me make sure you can see the entire Capstone screen here before we get started. We've already taken a look at the hardware setup panel. Let's direct our attention down here to the controls palette on the bottom below the main workbook space. And there we can see that there is a record button allowing us to record data from the sensor. So I'm going to set the mass in motion above the motion sensor and then just press the record button. And let's see what happens in our graph when I press record. We can see that there are dots, which is a data point. A position reading is represented by a dot. And by default, these dots are connected by lines to let us follow it a little better. And then as we see the graph go off past the 10-second mark, we can see that by default, the graph rescales to ensure that all the data is in view. But once we've collected all the data we want, we can simply press stop from the controls palette down at the bottom. And all the data we recorded between pressing start at experiment time 0 and stop at experiment time 20 minutes, 20 seconds, 20.2 seconds down here in the experiment clock. All of that comprises what Capstone calls a run of data. And we can see from the graph legend up here that it enumerates these runs. So by default, the first run is run number 1, and it has a unique symbol and color shown here in the graph legend. So we saw that the graph automatically scales the data to keep it in view, but we do have control over our view of the data within this graph display. So let me show you a couple ways we can manipulate our view. One is to simply take your mouse cursor, which looks like a hand, and when you click and drag, you can basically translate the graph in any direction, much like you're translating a piece of traditional graph paper, left, right, up, down. So if we want to focus on a particular part of the data, we can just pan it. So we're looking at that section. Another thing we can do directly in the graph that we can't do with traditional paper graphs is that we can rescale them as if they're made of rubber sheets. And the way to do that is to hover your mouse cursor over a number label on the X or Y axis, and you'll see you get a double-headed arrow. When you click and drag toward or away from the origin, you'll see that the graph stretches or compresses. And this all depends on where the origin is. So moving toward the origin causes compression, moving away from the origin causes stretching. So through a combination of stretching and compressing the axes and panning around, we can get the view of data that we want. Now, if you have a trackpad on a computer or a scroll wheel on a mouse, as I have here on my desktop computer, there's a fast way to really easily change your view of the data that I use all the time. And that is to take your cursor over the number labels on the axis and simply scroll in or out with your scroll wheel or trackpad scrolling feature. And you'll see that it scrolls in and out centered on that particular value of the x-axis or value of the y-axis. This scrolling technique also works in the middle of the graph to zoom in and zoom out to the particular data points that you want to focus on. So some easy ways to change your view of the data and look at exactly what you want. Now, oftentimes it's the goal to simply fill the graph space with the data that we've collected. So there's a shortcut for doing that. And that shortcut is contained in this graph toolbar. You may have seen this graph toolbar flickering on and off depending on where my cursor is. By default, when your cursor is off the graph, it hides it to avoid clutter. And when your cursor goes over the graph, it shows this graph toolbar. Since we're going to be focusing on it, though, I'm going to press this pin button in the toolbar to ensure the graph toolbar is visible for the rest of our time looking at it in this investigation. So each of the graph toolbar buttons has a tooltip. So if you hover over, say, the first button here, it pops open a yellow tooltip that tells you what's going to happen if you press the button. In this case, the first one says scale axes to show all data. This is what we call the scale to fit button. And that's perfect for changing my view so that the graph space is optimized. My data fills the screen. So I'm going to press this scale to fit button, and we can see that the graph automatically translates and scales the graph axes, so my data is filling the screen. If you look closely, I'll zoom in here, the scale to fit button is one example of many that is a two-part button in the graph toolbar. There's the action part on the left that scales to fit when you press it, and then there's an option drop-down on the right part, indicated by this little black arrow. I'm going to press on that little black arrow, and it shows us some options for that particular tool. In the case of the scale to fit button, there's only one option called auto scale from 0. So I'm going to select auto scale from 0 and zoom back out. And what this does is it ensures that whenever I press the left part, scale to fit, the option I selected on the right, including the origin, is obeyed. If I want to turn that off, I can turn that off. And now that scale to fit button is not going to include the origin. So it's one example of many buttons in the graph toolbar that have two parts, a main part on the left for doing the action and a drop-down on the right for selecting options. So let's take that logic and extend it to another button. The Greek letter sigma button here allows us to display statistics. I'm going to go ahead and press the left part, which will turn on the default statistics. Zooming back out, we can see that is the mean value for the entire run of data, position versus time. So the mean position is 0.26 meters. But this button also has two parts. And in the right part of the statistics button, we can choose which statistics are displayed visually. So let me turn on, in addition to mean, the minimum, maximum, and standard deviation. And we can see that all four of those selections are displayed here graphically on the graph. Now, may or may not be obvious, but it's important to note that these statistical analyses and many other whole run analysis tools apply by default to the entire run. So the max min, mean, and standard deviation shown here are for the entire run one, and that's without respect to whether you're looking at the data. So if I pan the data off the screen here, those still have the same max, mean, min, and standard deviation. So the statistics by default is analyzing the entire run. I'll scale to fit to get that back, but it's just important to recognize that tools like statistics apply by default to the entire run, whether or not you're looking at the run or all the data points in the run. Since it is a two-part button, I can toggle the display of statistics on and off with the left part. And you notice that this long tooltip tells me basically the left part before this little vertical pipe is display selected statistics for the active data. And the right part, the dropdown, is how I can select which statistics to display. So I can toggle it on and off with the left part of that button, and I can select what's displayed with the right dropdown part. So it's an introduction to the crucial feature here of many of the buttons in the graph toolbar, the two parts. All right. So let us continue here. I'm going to toggle off the statistics here so it's not being displayed. And I'd like to collect another run of data now. I'm going to remove one of the masses from the end of my spring. So I've gone from 200 grams down to a single mass, 100-gram mass. And I'd like to collect some more position versus time data after I set this 100-gram mass oscillating. Probably was slightly off camera for you, maybe peeking on at the bottom here. And I'd like to collect more data that shows position versus time for this new situation. So to do that, I'm going to go back down to the controls palette and hit the record button. Let's see what happens. All right, so in the same graph, I am getting a new set of data plotted on the graph of position versus time. You might wonder what happened to the other. If you notice carefully, you'll see this is offset, of course, because there's less mass, so the center point is higher, equilibrium point. But now that we have some data for run number 2, I'll press stop. And now let's ask the question, what happened to run number 1? Is it still in my file? Did I need to save it? Well, it's important to know that a display like the graph is merely a way to visualize data that's inside the Capstone file. And any data you have in the file fundamentally lives in what's called the data summary panel available from the tools palette. So I'm going to click open data summary. And this tells us that we have a wireless motion sensor that offers position, which we've seen, and in fact offers other measurements. And for each of these measurements, position, velocity, acceleration, it has collected the 2 runs of data that we expect. And run 1 is still in the file. It's just that somehow it's been hidden. We'll talk about that in a moment. But while we're on the sensor data summary, I'd like to make more descriptive names for my runs. So I'm simply going to double click on run number 1. I could delete the whole thing and rename it, but I'm just going to append to it something like 200 grams. And I'll hit enter. And when I do, it renames run number 1 for all of the measurements that had a run number 1. Similarly, I could come in and double click on run number 2 and call that the 100-gram run. And when I hit enter, you'll see it propagates that name change. And notice that since we are displaying that run in the graph over here, the graph legend reflects the change in run name in the legend. While I'm here, you'll see that Capstone picks a rainbow of colors. And unfortunately, it has picked 2 very close colors for runs 1 and 2. So one additional thing we can do here in the sensor data summary is to go in and change other properties besides the name. So I'm going to go in and click on the gear for run number 2, and I'm going to say, you know what, I think it would be easier to distinguish these 2 runs if I make that one red. Press OK, and in the background, we can see it made that change. So we have a blue run number 1 and a red run number 2 for position. Well, I've done with the data summary, so I'll collapse that in the tools palette. And let's now ask the question, how do we see both of these runs inside the graph? Run number 1 with 200 grams and run number 2 with 100 grams. And the answer is yet another button in the graph toolbar called the data selector. You may be wondering, how do you know the names of these buttons if when you hover over them, they don't tell you the name, they tell you the action in the tooltip? Well, a little trick here is if you go to the last button in the graph toolbar, this is for showing and hiding tools, but a side advantage of this is it actually tells you what the names of the tools are. And this can be helpful if you want to write instructions about them or look them up in the Capstone help. So I can see that this little rainbow triangle thing is actually called the data selector. And that's what we're going to focus on for figuring out how to visualize specific runs inside the graph. The data selector has 2 parts again, the button on the left and then the drop down. Here I use the drop down a lot more than the left part because when I hit a drop down, you'll see I have a choice of runs to make visible. So I'm going to click run number 1 and zooming back out, you'll see in the graph that has switched from run number 2 to run number 1. I could switch back, but you'll notice it's only showing 1 at a time. That's the default behavior of the Capstone graph, to show only 1 run at a time so things don't get too cluttered. But the purpose of the left part of that button is to allow simultaneous viewing of multiple runs. So if I press the left part now, I can go to the right, and now whichever runs I turn on are simultaneously visible. By the way, you'll notice there's a select all option there. If you want to just do those two steps automatically, pressing the left part of the button and selecting all the runs. But I think it's valuable to know what the left part does. That is, it makes uh, any run available to be visible, multiple runs at the same time. All right, so we have this sinusoidal-like curve. We can see the offset. We might begin noticing some other differences between these two runs, the 200-gram blue run and the 100-gram red run. One thing I might be curious to do is to say, you know what, this looks kind of sinusoidal, but maybe it's tailing off a bit. So I might want to fit this to a mathematical relationship. So I'm going to go to another tool here in the graph toolbar that has two parts. This tool is kind of interesting because it's already on. The left part of this curve fit tool is depressed already. But the reason we don't see a curve fit yet is that we haven't selected one from the right drop-down portion. So if I click the right drop-down portion, you'll see that there are lots and lots of curve fits that we can apply to data to try to figure out relationships between variables. In this case, you can even have user-defined fits if there isn't one here among the 17 or so that you like. In this case, I'm going to choose a damped sign fit and see if that fits the data well. I'll move the legend out of the way here. And if I stretch this, you can see that looks like it does a pretty good job, almost hard to see since it matches so well with this red run. And here's the equation for this damped sign fit relating the position y against time, the x. So we see these parameters and we can get the angular frequency off of this, 8.14. Now, one thing you might be wondering is, why did it only turn on a curve fit for the red run number 2? Well, the answer is there's only one toolbar for multiple runs. So when we have multiple runs, we have to be cognizant of only one run being active at a time usually. And by default, it's the most recent run. How do we know which run is active? Well, if we look at the graph legend here, you'll notice that run number 2, the red run, has a shaded background behind its symbol. That indicates it's the active run. And only active runs are analyzed by tools like the curve fit and the statistics we saw earlier. So what if I want to make run number 1 active in order to analyze it with a curve fit? Well, I can make a run active two ways. I can click on its symbol in the graph legend, and you'll see its background becomes shaded and run number 2 becomes prominent, indicating it's active. There is another way to make a run active, and that is to click directly on a data point of that run. So I'm back on run number 2 being active, and to make the blue run number 1 active, I can click on it, and you'll notice it makes that shift to being active. So now when I go to the graph toolbar again and turn on a damp sign fit, it is now applying to the blue run number 1 because it was the active run when I turned on the tool. All right, so we could go ahead and do a comparison of the angular frequencies here. Hopefully there's a square root of 2 factor in there somewhere for the doubling of mass. But you can see that we can pretty quickly visualize data from a sensor and do some fairly sophisticated analysis of it using that sensor data approach in PASCO Capstone. Now, a couple more things before we wrap up this activity. I want to turn off the visibility of these curve fits, but there's a little shortcut here. You might realize that I would need to turn it off for the blue run and then the red run, but it turns out many people don't know this, but you can make multiple runs active in a graph at the same time. One way to do it is to shift click on another run's symbol. Another way to select all of them is to simply hit the symbol in the header of the symbol column, X in this case for position, and that makes all the runs active. So now a single press here of the curve fit button toggles off or on the curve fits for all of the active runs. All right, so I'll go ahead and toggle those off. And you might remember in the data summary that the motion sensor collected not only position data, but also velocity and acceleration data. We can visualize those by switching our graph axis to a different measurement type. So you notice the y-axis measurement is position in meters. Both of these things, the position label and the meters label, are actually buttons, and we can change the units or measurement being shown on it by clicking on that. So I'm going to change the y-axis from position to velocity. And there we can see the velocity, that is the drive from the position versus time data. We could similarly change it to acceleration. But I want to show you that despite the graph defaulting to time on the x-axis, the x-axis label is also a selector of measurements. So I could switch the x-axis from, say, time to something like position. And now if I scale to fit, you can see that we have something like a phase plot for both of these runs. All right. Little bonus here. Make sure you can see the entire screen. Capstone was really focused on recording data, but the controls palette actually has a playback mode indicated by this little green play button. And when you go to playback mode, you can actually play back the data and something complex like a phase plot can be visualized in real time by default, or you can go ahead and do slow motion or fast motion. So for activities where it helps to talk about the data as it's being played back, you can go from record mode to playback mode here in the controls palette. All right. So I've saved my favorite capstone feature for the last in this case, and that is I've done a lot of investigations here. I've changed a lot of things, but I may want to go back to a prior state. And you can do so easily in Capstone because it has unlimited undo. And to access this undo, there are a couple ways to do it. You can go to this blue arrow on the top bar, and it tells you in the tooltip, this will undo start playback. Similarly, you can go to the edit button and press undo start playback here, or I use undo so much, I'm just going to remember this keyboard shortcut, Control Z on Windows, Command Z on Mac. And when I press Control Z, you're going to see it steps back step by step, everything I've done in this file from the start. So if I press and hold Control Z, it can go as far back as I want. And if I want to go forward, there is a redo button whose keyboard shortcut is Control Y on Windows or Shift Command Z on the Mac. So I'll press and hold Control Y, and you'll see it'll zoom all the way back to the end. So I'm going to go back a few steps with Control Z, and I want to end this file looking at the positions for both of these runs, position versus time. All right. So before we get to some of your questions, I want to show you one important thing. Once you've done some work of collecting data and doing some visualization and analysis, we want to figure out how can we preserve the information in the capstone file. So today I'm going to talk about three things we can do. The first of which is the most fundamental, and that is we can save the capstone file as a .cap capstone file. So let me show you how to do that, and I'll talk about what we get as a result of this. I'm going to go to the File menu and choose Save Experiment. And if you're showing extensions, you'll see that capstone files have the extension .cap. So I'm going to go to the desktop here, and I'm going to call this Mass on Spring with data. And when I hit Save, it's going to append that .cap extension on it. I'll go ahead and close Capstone and bring this file over to the desktop that you can see. Here's the Mass on Spring with Data Capstone file. And although I created this file on my Windows computer, it can be sent to anybody else. If Alec was on a Mac, I could send it to him. And as long as he has Capstone, he can open this file. I'll go ahead and either double click on the file or go into Capstone and choose File Open. I'll double click, and since .cap files are associated with Capstone by default, it goes ahead and reopens that file in the state that we left it, right? So all the data, displays, settings, analyses that we left the file with are still in the file when we open it. We could reconnect to sensor, collect more data. We could do analysis outside of the laboratory. So there are many reasons to save a capstone file, but fundamentally saving a capstone file, although it requires capstone to open, does open across platforms and preserves everything about the file. All right, so that's the first example of saving and sharing that we'll talk about today. We've covered quite a bit in these few minutes. We've covered pretty much the fundamentals of how do I connect a sensor and view data and do some basic run-based analysis. We figured out the sensor data path is a great way to see a graph of the primary measurement. We've connected a wireless sensor in the hardware setup panel that popped open for us automatically. We've recorded 1 and then 2 runs of data. We've moved and scaled the graph manually and with scale to fit. We've analyzed run statistics using those 2-part buttons. We've renamed runs in the data summary and even changed its color. We've changed the run visibility in the graph display using that data selector button. We've applied a curve fit to each run and known that we can make a run active in order for the curve fit to apply to it. We've even changed graph axes, undone multiple steps, redone them, and saved the capstone file. So I want to pause at this point and ask Alec to survey whether there's any Q&A we can address in a moment. While he's doing that, let me talk a little bit about sensors for PASCO Capstone. You may have noticed that I was using this white sensor from our wireless line of sensors using Bluetooth low energy. But PASCO Capstone has been around a while, and PASCO sensors have been around even longer than Capstone. So I want to assure you that PASCO Capstone works with wireless sensors. It also works with our blue passport sensors. I'm showing an example of the motion sensor in each case, both on the screen and here in real life. So blue for passport came out in the early 2000s. And even back to the last millennium, we have the Science Workshop sensors. And all of the sensors in all 3 of these lines are still supported by PASCO Capstone. So it's important to note, though, that although the wireless sensor can connect directly wirelessly or via USB in many cases to the computer, the Passport and Science Workshop sensors don't have direct computer connections. So in each of those cases with Passport and Science Workshop, you will need to connect via an interface, and these can be as small and simple as an Airlink, which essentially makes a passport sensor into a wireless-like sensor, or as sophisticated as our 850 interface, which accepts multiple Science Workshop sensors, both digital and analog, and multiple Passport sensors. All right, you can learn more about Pasco sensors at pasco.com/sensors. Bottom line, we support connecting all of these sensors even back to the past millennium. And those sensors, if you have them still, are probably older than the students who are using them on average. All right, so I want to pause here. Alec, any questions we can address to the entire group?
Yes, we had a question from John about how you could zero the motion sensor to show it oscillating around zero. You
Ah,
mentioned
yeah.
we
So
can do that in the calculator. I wonder if you could demonstrate that.
yeah, so there are a couple ways that we could do that. In the next activity, I'm actually going to show you how you could zero a force sensor using a zero button, which is unavailable here for the motion sensor. The way the motion sensor works, I didn't mention it, but it has kind of like a bat or a dolphin's echolocation. It sends out little ultrasonic chirps. There's a side effect where you can hear when the chirps are sent. They bounce off an object that's large enough, and in a straight line, even this very small mass is large enough to bounce back enough sound. It detects the echo, the return echo, given the speed of sound, calculates the time, and from that it can determine the position and velocity acceleration. We have a little dilemma here in that there isn't a zero button available. There is for force sensors, but there isn't for motion. So I'm going to take Alec's suggestion here. And remember earlier we found that we could, for example, take the mean of a run. So I'm going to do this for the second run number 2. I'll turn off run number 1 to not distract us. So what I want to do is figure out, well, this is probably oscillating around the center point. And if I wanted to define that as 0, I first want to find it, and then I basically want to transform this data so that all of these readings are subtracting off that value of the position of the 0. So first, let me turn on the statistics, and we can see the mean is 0.45. So that's the value I want to have in mind. And now you can imagine going through and subtracting off 0.45 meters off all these values. There is a tool in Capstone, a fairly sophisticated tool, that allows us to transform incoming measurements and basically output another measurement after the fact or even live. It's what Alec mentioned, the calculator. So if I open the calculator here in the tools palette, you'll see that it has basically a blank here. And the way the calculator works is kind of like a programmatic assignment. And I want to say that I'm going to call it offset position equals. So basically the output of this is going to be what's on the left of the equal sign, and the transformation, the mathematical transformation is going to be on the right side. So I want to basically subtract off 0.45 from every position measurement. So I've typed in 0.45. You get a better view here. Forgot the decimal place here. 0.45. All right. So what do I want to put in front of that I'm subtracting 0.45 meters off of? I want to put not just one position, but every position reading coming from the motion sensor. And the way to do that is to go down to the calculator here, and there's a little data selector button, the same icon we saw on the graph toolbar. If I press that, I can insert any measurement coming from any sensor. So I'm going to insert position, and it tells me that it's not just one position value, but all of them by showing me these little brackets. Those are inserted automatically, but it's good to know that that's why they exist, because it's going to take every position measurement and subtract off 0.45 from it. I'm going to go over here, and the last thing I want to do is define the units of this offset position as meters. So I'll go ahead and hit enter. And now what happens is basically anything that comes in as a position gets transformed into an offset position. So I'm going to go and close the calculator. And now if I go in here and switch the y-axis measurement from position to offset position, you should see that it's now centered around 0. So that's a powerful feature of the calculator. Take incoming measurements from sensors and transform them, in this case, fairly simplistically by subtracting off 0.45 meters to effectively get an offset. What I want to show you, though, is the real power of the calculator is this can happen live. Now, because I closed my file and reopened it, I do need to reconnect my motion sensor. So I'll go ahead and into hardware setup again and reconnect my motion sensor. And let's see. Oh, Capstone didn't like that. So sorry, let me start again here. So with the motion sensor, reconnected. We'll go ahead and redo that calculation. All right. So we had a graph of position versus time. We still have the same offset, thankfully, so I can press record. There's the non-offset value. And if I go into the calculator, set position is equal to all those positions. Power user shortcut, remember those brackets? If I just press a bracket, it will open a pop-up menu from which I can select those things automatically instead of going down to the buttons. And I was subtracting off 0.45, and the result is in meters. All right, so sorry, we've just redone that. So what happens is there's now a new data set here in the data summary. It's under the calculator tab, and it's basically taking every run of position and giving me a new run out of the offset position. I could switch my graph from the original position to the offset position, and here we can see it centered around 0. What I find really powerful about the calculator, though, is it can be doing the transformations live. So let me simply press record, and now it is recording new data live from the sensor and doing that offset calculation live. So we're getting that offset taken off automatically via the calculation. Power user tip, you may be interested in looking at both the offset position and the position at the same time. We're going to learn later we can have multiple graphs, but a useful thing that someone taught me at PASCO is if you have two like measurements, say position and offset position, and you want to see them both on the same set of y-axes, instead of switching between them on the y-axis label, there's actually an option called add similar measurement, and that allows you to turn on multiple at the same time. And now we use the graph legend to distinguish between them because the y-axis has become a generic position from all possible position sources. And now if we hit record, we can see both the original non-offset position coming live from the sensor and the live transformation via the calculator. So thanks so much for that question. Really powerful feature of the calculator. And thanks for suggesting it, Alec. All right, let me see if there's some other things we should look at here. I think for the sake of time, we've hit that graphing similar measurements. Let's go ahead and proceed to the next activity. Alec is ably taking care of those questions. Thanks for asking them in Q&A. Keep them coming. We will address them as a group after this activity. All right. Alec, as I get set up, is there anything you want to mention to everybody verbally as I switch over that has been asked?
No, I think we've got all the questions answered
All
here.
right.
There was a question about the difference between zeroing it using the calculator and using the button that's on some of the sensors. But I think we'll see that in the next activity.
Indeed, we will for the force sensor, which has a hardware zero or a software-based zero that will basically do that calculation of offsetting automatically. All right. I guess one side result of using the built-in zeroing is that you don't get the original, you only get the output data, which is usually what you want to keep things clean. All right, so let me show you the sensor we're going to use for this next activity. It doesn't quite look like a sensor, but it is a wireless sensor. It is a wireless suite of sensors on low friction wheels called our smart cart. The smart cart has a lot of measurements we'll see in a moment, but it can measure position, velocity, acceleration, as the motion sensor does. It can measure force. You can even measure 3 axes of acceleration and the resultant and angular velocity via gyroscope positioned here in the sensor where this XYZ axes are to help indicate the directions. You'll see there's a plus X indicator on there. We will need to recognize that in a moment once we set things up. But all I've done in this case is I put a little spring bumper on the force sensor of the cart in order to be able to do some collisions in this track over here. And what I'm going to do is basically put a small mass on the cart, and I have that spring bumper on the end connected to the force sensor. I'm going to push that spring bumper into the wall, and we're going to ask some questions about it. How can we control the sampling options to ensure we're capturing the data of interest that we might want to analyze impulse and compare it to momentum changes? And second question, how can we analyze that data in depth to see if there is indeed a relationship between these two? So we're going to return to Capstone, and we will shortly be featuring the zero button. So I'll go ahead and close Capstone completely. Don't need to save that file. Launch it again. And this time, instead of using the sensor data option, we're going to take more control over the setup. So the way we're going to do that is start by acknowledging that we want to connect this smart cart. We can do that by ensuring that the smart cart is powered on. It is just another wireless sensor. And I can go directly to hardware setup, and I should see it advertised with its 6-digit ID right there. I'll go ahead and click on it to connect to it. And once it's connected, we're going to get a view of all those sensors that are actually built into this cart. There are 4 different sensors, most of which offer multiple measurements. And one of the things we might want to do is reduce clutter and focus on data transfer for the data we actually want to investigate impulse and momentum. And in order to do that, we're not going to need the acceleration, which is XYZ acceleration resultant, and the angular velocities. So to save bandwidth, I'm going to go and turn those sensors that are inside the cart off so that we're only getting readings from the position sensor, which gives us position velocity acceleration from the wheels, and the force sensor, to which I have the spring connected. If you don't know what measurements these are going to produce, we can go to data summary and see those measurements listed under each of those sensors that we've kept on. So this is going to keep our file clean and also preserve all the Bluetooth bandwidth for the measurements that we actually want from position, that is velocity, and the force sensor. All right, so we've done the hardware setup there. I'm going to go ahead and now go over to the displays palette on the right side. And I'm interested in a graph because that's great for visualizing. And if I hover my cursor over the graph icon in the displays palette, I see that there's a tooltip that says either drag to the page or double click to create a graph display. So although we could use these little quick start buttons, we can ignore them completely and just double click graph to tell Capstone what we want is a graph. In this case, we need to select what measurement we're looking at on the y-axis. I'm going to start with force. And as we saw earlier, it defaults to time on the x-axis, which is fine. So what I want to do is just collect some force data and ask you whether you think it is properly characterizing the brief collision that happens between the cart with its spring and the wall at the end of this track. So I'm simply going to press record, push the cart, let it collide, bounce back, and hit stop. And I'll scale the fit, and here is our data. I invite you in the chat to share any criticisms, compliments of this data. The real question here is, does this force versus time data represent the forces experienced by the cart when it collided with the wall at the end of the track? Let me know what you think in the chat. All right, Marie says you need to increase the frequency of collecting data. Yeah, notice that we have a small force here. That must be after I push the cart. And then we have a very large negative force. You might ask why negative? Remember that positive x direction in your view right now is to the right. So if the force is applied to the left, it's going to be negative. We could change that, but for consistency between measurements, I'm going to keep it as negative. But as Marie notes, we only have one data point here during the collision. So we don't know what happened between that one data point and the previous, which was nothing, and the next, which is no force. So we definitely want to better characterize this collision by getting more data during the collision itself. I don't think one data point properly represents it. How do we know we hit the center, for example? We probably didn't by chance. So we want to increase the frequency of sampling, as Marie suggests. Any other criticisms of this data? I might zoom in here to give you a hint about that. What do we want to be defined as no force on the cart? Probably when the cart is stationary or not colliding, right? We want to define that as 0. Now, to be fair, it's not that far off. It looks like it's offset by a little over positive 0.1 newtons. But this is something we probably all eliminate if we want to do some very fine data analysis. So scaling back out to fit. Now we can look at the controls palette at the bottom and look at the way to zero many sensors that support it directly. And that is, instead of doing a calculation, we can simply press this button when we have the right measurement to zero the sensor now. Now, in order to make sure we zero the right sensor, though, we have to look at this entire section because we have multiple sensors now. So we're going to do 2 things here. We're going to take Marie's suggestion to zero the sensor, the force sensor, but we're also going to make a decision about how frequently we collect data from these sensors. So let's start with the force. I'm going to go to force, and I'm going to press the zero sensor now button because I'm not applying a force to the cart. And that's going to redefine whatever force was being measured at that moment as 0 newtons. So that's covered one of the 2 things. The other is that we need to collect a lot more data over this short time period. And we can do that by adjusting the force sensor's sample rate. Now, when you have multiple sensors, there is an option here for a common rate between all the sensors, But I chose this experiment, impulse and momentum, because it's one example when it's really handy to have completely different sample rates for the two different measurements. In this case, for the force sensor, I need to sample really fast. And I can dial up this arrow here. You can see it jumps. And in this experiment from prior experience, I think something like 500 hertz would be good. By the way, you'll see I can go even faster. I can go up to 2 kilohertz. I can only go faster because I turned off those acceleration gyroscope measurements that I didn't need. So it's going to make sure that we have the bandwidth to transmit this force sensor data. For the position sensor, from which we're going to get velocity, I'm going to press the smart cart position sensor, and I'm going to dial that up a little bit, maybe to about 50 hertz, so 1/10 of the sample rate of the force sensor. And that's fine because I'm only interested in what's the incoming velocity and what's the outgoing velocity before and after the collision. Whereas with the much faster sampled force, I need that high sample rate to determine what's happening during the collision. All right, now that I have those things set, thanks Marie for the suggestions. I'm going to delete this last data run, run number 1, and there's a handy way to do that from the delete last data run button in the controls palette. And I think I'm more prepared to collect the data. Let me just test it. I'll hit record, and we're hoping to have a 0 value, looks good, and many more data points during the collision. So scrolling at that point, looks like we have quite a few, and we're better characterizing what happens to the forces on the cart during the collision. All right, let me delete that one because we're not only interested in force, we're also interested in ultimately momentum, but to get there, we can use velocity. So we know we can get velocity from the smart cart's position sensor on the wheels, but we need a way to visualize it. And so far, we've only looked at the ability to either switch measurements, say to velocity, or to add similar measurements, but force and velocity are not similar, so we can't overlay them. So the answer is going to lie here in the displays palette. We could double click to create another graph, and I could say, you know what, I want this graph to be force, but I don't think this is the best way to view it because we have disconnected axes, and our view is not necessarily going to line up left and right. To be fair, this will work fine, but I don't think it's the best way. So let me Control Z, undo that, and come back here where you might say, well, the other option for displays is to click and drag. So if I click and drag below, I can get a forced graph on the bottom. But once again, although they're aligned vertically, the time axes are independent of each other. So let me undo that and show you that a single graph display, which we have already, has the ability to show multiple plots inside it. And the way to access that is to go up to the graph toolbar, which I'll once again pin. And there's this button here called, zooming in, it allows us to add a new plot area to the graph. It looks like XY axes with a little green sparkle. So zooming back out, I'm going to add another plot area, and you can see that it shows me a new plot area below. I'm going to make that show force. And now the beauty of this second plot area, and you can have multiple plot areas beyond 2, is that we have time synced x-axes. All right, so they're always going to remain aligned. All right, now I think I'm ready to collect some data. So let me go ahead and press record. We should see both velocity in the top plot area and force in the bottom plot area. And I have zeroed the sensor already, so I'll press record. All right, and now I can zoom in to the point of interest. And on the top plot, we can see the positive velocity cart collided and then exited with a negative velocity, opposite its plus x direction. And at the same time, we had a force applied in the negative direction of the cart to cause that change in velocity. All right, so the real question here is how can we get changes in momentum and the impulse out of these two plots? Let's start with the top plot. I'm interested in asking what was the incoming velocity and what was the outgoing velocity so we can figure out the change in velocity that was caused by this applied force over time. And we could read values off the graph axes, but of course, there's a tool that'll let us do this more precisely. That tool is a new one, and this is the first tool we've looked at that applies to single points. It is called the coordinates tool. It looks like a crosshairs. If I click on the coordinates tool, I'm going to choose the first option to simply add a standard coordinates tool. And I'm going to be disappointed because, it added this coordinates tool to the force plot area. Why did it do that? I don't think it should have because don't I have the velocity as an active measurement? Well, I do, but now we have the concept of we have active measurements indicated by the graph legend. We also have active plot areas, and you notice that only one of these plot areas has a cyan border around it. That cyan border indicates it's the active plot area, and that's the plot area that tools apply to. So I'll undo that. I'll click on the top plot area. You'll notice as I alternate my clicks, the plot area that I click on becomes the active plot area. And now when I turn on the coordinates tool, I get a coordinates tool that basically jumps onto a data point and through this little tail and annotation tells me that this data point right here where the crosshair lies is at 1.9 seconds and the velocity was 0.497 meters per second. I can move this around. I might move it here by clicking and dragging, and it will snap to the nearest data point. I can also nudge it left and right with these arrows, or even with the right and left arrows on my keyboard. So I'm going to put that right before the collision. So incoming to the collision, the cart was traveling a positive 0.492 meters per second. And I could add a second coordinates tool via this, but there's a quicker way. I can go directly to a data point and click on it, and it pops open a number of tools that are appropriate for single data points, including coordinates, an annotation if I want to write a little note, and even a slope tool. I'll turn on coordinates tool again, and we can see the outgoing velocity was a negative 0.452 meters per second. Now, if you like shortcuts like I do and don't want to do this math to figure out the change in velocity, I'm going to delete the second coordinates tool because every coordinates tool has hidden up its sleeve a subtool called the delta tool, Greek letter delta for change. So on the first coordinates tool, I can click on delta, and I can grab this second handle and basically drag it out to any other data point, drop it, and Capstone will tell me what the change in x, the time in this case, and the change in y, velocity, are automatically between these two handles. So negative 0.944 meters per second was the change in velocity for this cart from the incoming to the outgoing. Now, our analysis to get impulse on the force versus time graph is a little more complex. How do we get impulse? Well, that's basically an integral, right? It's an integral of force over time. So when we talk about integrals, we start to talk about the area tool, a tool that applies to entire runs by default. So with the bottom plot area active, I'll turn on the area tool, and it shades in the area between the plot and the y equals 0 axis. We have to be a little careful here. Notice it's doing it for the entire run. So maybe this doesn't matter too much, but if I want to constrain a run-based analysis to a section of the run, we need another tool that allows us to basically say, only analyze this part right here. And that tool is a new one in the graph toolbar called the highlighter tool. So I'm going to press the highlighter, which looks like a yellow marker, and it drops a highlighter on the graph, the correct plot area. And notice that I can change this highlighter. And as I move it around, two things happen. All the data points inside the highlighter box turn yellow, indicating they're highlighted. And then more importantly, the area tool, notice, updates so that it is only analyzing those data points that are highlighted. So here, I think, is an appropriate analysis for the area, quote, under that curve. It's above it, that's why it's negative, but area under the curve can be accomplished via the area tool. And importantly, a highlighter that allows me to analyze only a section of the run. So with those two things, I'm going to say, add a table by double clicking table. And I can start to go in here and say, you know what, for some user entered data, I'm going to say this was a hard spring slow collision. And I can say this is some user entered data, not coming from a sensor, but something I want to define. And this is the trial. And I can similarly, in this table, begin adding columns that allow me to take this metadata from my analysis and begin to compile them inside Capstone. So I might say, well, in this trial, the change in velocity was 0.944. That is change in velocity. Here's a trick. If you right click, Capstone shows you some special characters. So I can get delta. I can name this whatever I want. It is simply user entered data. Try tab, that's meters per second. And similarly, I can start compiling the corresponding impulses, in this case, negative 0.49, and call that impulse. I'll abbreviate that J and call that, it's going to be Newton seconds. All right, so you can see I can actually begin to make these measurements that I'm getting off of graph analysis tools into hard data that I can analyze. Now, because we're short on time, I'm just going to go ahead and close this file. And I've already earlier today collected 6 runs of data where I've varied things like what spring do I have, hard, soft, clay bumper, and I've varied the incoming speed. So I have 6 runs of data. I've simply continued that process of collecting a run, doing the analysis, and typing it into the table. So here are those 6 runs. I could show all of them at the same time here if we wanted. And now you can see why we only show one at a time by default. But I have all that data in this set over here. And now I want to do some analysis on this metadata. And I'm going to do that on a new page because I've kind of run out of room here. So I'm going to click on that table on the edge to make it dark blue. I'm going to hit Edit Copy and build a new workbook page. I'm going to paste it, Control V. And let me bring that over. And I now have this big space where I think it would be great to graph this data that I typed into the table. So I'm going to drag a graph there. And I'd like to plot 2 user entered data sets, the impulse J versus the change in velocity. And that's looking pretty good. I'm kind of annoyed by this connecting line. So In many places in Capstone, you simply right click and it gives you some options. I'm going to turn off the connecting lines. And now we're at the point where we can say, this looks like a linear relationship. I can go to the curve fits, turn on a linear relationship, and begin to discover that, it appears to be a linear relationship between the impulse and the change in velocity. And if I look at the units, those units are kilograms. And by the way, the cart's about 250 grams and the mass I added is about 250 grams. So we seem to be discovering that the constant proportionality between impulse and change in velocity is the mass of the object. Right? So kind of a discovery-based lab there. All right. So we are nearing the end of our time. I'm going to zoom forward here, and I will come back. If you have to leave, there'll be in the recording some additional content there. But I want to show you that you don't need to make up your own labs. Capstone, as we saw, allows us to. We can build our own labs via the sensor data path or by taking our own control over displays. But we can also do quick starts. So if you go into Capstone and connect something like a smart cart, at the bottom of that workbook page, you'll see options like momentum and impulse, and that will set up some basics of the file. But there are full files ready for you and your students in our experiment library at pasco.com/free labs. And if you search for something like impulse using the smart cart, you'll see this lab. And one thing that's interesting about Capstone labs is, especially at the university level, they often come in two formats from our free experiment library. There's a PDF where students can follow the instructions, or there's actually a Capstone workbook where all the instructions and displays are contained inside the workbook. All right. So since we've officially reached the end of our time, let me go ahead and wrap it up formally here. If you have any questions, we invite you to contact your PASCO rep via the link at the right, pasco.com/support. On the previous slide, you might have noticed that we have basic files available for students on our free experiment library at pasco.com/free labs. We have additional files like graphics, sample data files, editable versions of the experiment on our PASCO portal, which is available by subscription. If you want to get a free 90-day trial of PASCO portal and have access to all those experiment files, you can do so by following the link at the left, pasco.com/portal-free-trial. All right. So with that, I'm going to formally wrap it up. I will zoom back here to do a couple additional things. But before I do so, Alec, any questions we should answer as we wrap things up? If you need to leave, I want to thank you for joining us and invite you to fill out the survey that will be available when you close the Zoom webinar interface. Otherwise, we're going to stick around for some Q&A and some potential additional topics, and all of this will be in the recording if you need to leave us right now. If you do need to leave us, thank you so much for joining us, but we will continue with a little bit more content if you're able to stay with us. Alec, anything we should address to the entire group?
Not yet, but
Not yet?
feel free to type them in the chat window or the Q&A if you have any.
Awesome. Thanks for being here if you have to leave. So in the second activity, we figured out how to manage our sensor measurements, sample rates, turning measurements we don't need off. We've zeroed the measurement directly for sensors that supported in the controls palette. We figured out we can delete runs after we've done some trials. We've arranged displays, creating new ones. We added a graph plot area to ensure that our two measurements stayed in sync. We made graph plot areas active so that the tools like curve fits and coordinates tools would apply to them. We did some analysis with coordinates and delta tool, did area under the curve to figure out that integral for impulse, and we analyzed only a portion of it with that crucial highlighter tool. Then we created a new user table that allows us to summarize our own user entered data, and we put that on a new workbook page so that we could graph it. And one thing I want to circle back to ensure we cover, though, are a couple more options for sharing things from Capstone. All right, so one thing we can do in Capstone, besides saving the Capstone file, and by the way, I will do that directly here, just to preserve it. This is impulse momentum analyzed. I will be saving all these files and sharing them via a shared Google Drive folder. I'll show you the QR code in a moment. Now that I've saved this file, though, I might want to put, say, this graph, my final results in a lab report. So I'm going to click on its border of the graph display inside Capstone, and then I can go to Edit, Copy, and now I might go over to, say, a Word or a Google Docs lab report, and I can choose Control-V or Edit Paste, and I get a static image of that Capstone display deposited directly into that. Now, it's important to note this is a static image, so I can't go in here and adjust things, but I can go, and that's why I always save the Capstone file. I save the Capstone file, so if I want to go back and change my view or adjust what's being analyzed, I can do so in the live Capstone file. So copying and pasting images, especially of graphs, into other document formats is a great way to make lab reports, for example. One other thing you may want to do, perhaps less often, but you can do, is maybe I just want my data into a spreadsheet program or another data analysis tool. So I'm going to select all the cells in my table, or in fact, press Control or Command A to get all those cells. Then I'll go to Edit, Copy. And now I could go to something like Google Sheets or Microsoft Excel. And because that's in my clipboard, I can paste that data directly into Excel. Now, that works for data that you see in a table, but if you ever just want to get all the data you can out of Capstone, there is a file menu option called Export Data. And when you choose File Export Data, it gives you the opportunity to choose which data you want to export by measurement, by run, and you can basically toggle off the things you don't want. Maybe I only want the raw sensor data. And then under export format, the default is comma separated value. And I can export that all to a file, which I'll put on my desktop, Capstone data, impulse momentum. It saves it with the .csv extension. On my computer, this happens to be associated with Excel. So if I go look at the desktop, I can see that I have this CSV file, which on my computer, if I double click it, opens in Excel. And now I have all the data that I chose to export in Excel, but notably only the data, nothing about the displays, nothing about the analysis I did outside of the data collection. But if you ever want to get data out of Capstone, the export data option from the file menu is a great way to do so. All right, well, thanks for sticking around for those additional options. Alec, any other questions we should address?
No, it doesn't look like we have any.
Okay, let me wrap it up formally then by saying, if you want the files from this, you can go to a shared Google Drive folder, tinyurl.com/introcap25. My slides are there with the links in the slides. The files I've just saved will be there. And if you're up for a challenge in Capstone, there's a file here called Freezing and Melting Data Challenge. The first page of this multi-page workbook lists the conditions on which the data was collected and some challenges on the right of things to do to practice the Capstone skills that you may have learned today. Thanks for pasting that in the chat, Alec. And then the challenge is up to you to follow in Capstone and try to do the things listed on the right side there. Most of those will be review of things that we covered today. A few things will be extensions like adding an annotation, a text annotation. But with that, I'll go ahead and end the recording, but we will stick around as long as you who have joined us live have questions.